All right, welcome back to another episode of Science with Surbeck. Today we're going to be talking about section 6.3, which deals with periodic trends. The objectives of this lesson is to compare period and group trends of several properties and to relate period and group trends in atomic radii to electron configuration. So we start out by talking about what our atomic radius is. And what the radius is it's measuring how close a atom lies to its neighboring atom. All right. So now a little bit different definition for metals and nonmetals. For metals, it's considered half the distance between two adjacent nuclei of a solid metal there. And for a nonmetal, it's half the distance between two nuclei of identical atoms. Okay, so all this is saying in terms of radius is just saying, okay, our radius is another way for saying size of a standard element, or of that standard atom of an element. Okay, now this trend is directly influenced by electron configuration. As we get more and more electrons added, the radius is generally going to expand, and we'll see how that trend plays out here in just a second. So with our atomic radius, we have this. As we move left to right in one period, there is a decrease in the atomic radius, okay? Now, the reason that there is a decrease is because there's an increased positive charge in the nucleus. What that means is we have more plus stuff pulling in those particular electrons on the outside. So as we move left to right, and you can see it's a really good picture down here in the bottom right, there is more positive pull to pull those electrons closer. That's what we call that electrostatic interaction between the positive nucleus and the negative electrons. Okay, so again, left to right in one single period, the atomic radius is going to get smaller or decrease. Now, with a group, as we move from top to bottom in a group, our radius is going to increase. The biggest reason for this increase is as we go further and further down a group, the energy level is increasing and increasing. So what that does is it essentially adds layers to the outside of the atom. And as you add layers to the outside of the atom, your radius is going to increase. So again, as we go down one group, your size or your radius of your atom is going to increase. And again, looking at this picture is a great way to see that trend in atomic radius. Now, we need to talk about another type of radius, and that radius is an ionic radius. So first off, what is an ion? So we start here with what an ion is, and an ion is just an atom with a positive or negative charge. Now, you may be wondering, okay, well, how did an atom get a positive or negative charge? And they did it by one of two ways, okay? One, they either lost an electron, or two, they gained an electron. Now, both of these things, to become an ion, both of these things require either getting more electrons or losing electrons. Key word here is electrons. All right, so if you lose an electron, remember an electron has a negative charge, so essentially you're minusing a minus, you end up with a positive charge. So if you lose an electron, you end up with a positive charge. Now, if you lose an electron, you're losing those negative things the nucleus has to pull into the center. As a result, an ion of a positive charge atom is a lot smaller. You can see the difference between a sodium atom and a sodium ion. The ion over here on the left is much, much smaller. Now, on the flip side, if you gain an electron, you are adding a negative charge particle. And so what that does is causes a negative charge to be considered on that atom. Now, what happens here, if you add another negative thing, we didn't add protons, so we add electrons, and that ion gets bigger. So chlorine's atoms on the left, the ions on the right, you can see by just adding that one electron there for chlorine, the size or the radius of that atom gets significantly larger. All right, so let's go through this and let's talk about our ionic radius trends. And we're going to break it down in between positive and negative ions. So for positive ions, as we go across one period, and remember, we're only talking about positive ions, and so for positive ions, we only go from lithium to carbon in period 2 because those are the atoms or the elements that lose electrons to be positively charged. What happens is the ionic radius gets smaller or decreases as you move left to right. Now for negative ions, again, period 2 example here, going from nitrogen to fluorine, these also get smaller or decrease from left to right. Okay, so key thing, ion, you're exchanging electrons, you're either giving them away or you're gaining them. That affects your charge. That's going to affect this trend here. Now going through this again, just talking about our particular ions, for a positive ions, as we move down a group, the ion size is going to increase. And you can see this picture with the purple showing the size of the ion. As we move down a group, it gets larger and larger. Same thing happens with negative ions, not as noticeable, but it does increase. It does get larger as we move down that periodic table or as we move down that group. Now, this sums it up really nicely, and we blow this up here at the end, but from left to right, positive ions decrease in size, negative ions also decrease, and ions as we move down a group will increase. That chart is really handy as we're going through more and more problems. All right, so we move to another item that we need to understand before we go through the trend. And that property there is ionization energy. And so ionization energy is the energy required to remove an electron from a gaseous state. So things that want to get rid of their electron are going to give it away for less value than things that want to keep their electrons. So something that has low ionization wants to get rid of their electron. Something with a high ionization wants to keep their electrons, and it's likely to form a negative ion. Okay? Now, with our ionization energy, we can have multiple per atom. This statement right here, what it's saying is it's named for the number of electron that is removed. The first electron that's removed from an atom is going to be the first ionization energy. Now, if we remove a second electron, it is considered a second ionization energy. That's all that means there. Once we start removing more and more electrons, it's going to become harder to remove those electrons, requiring more energy because we're getting closer and closer to that nucleus. So there's a stronger hold on those particular electrons. Okay? So now let's go through the trends here. Now that we know what ionization energy is, let's talk about the trend for ionization energy. So ionization energy, as we go from left to right across a period, the first ionization energy increases. So again, left to right, the ionization energy increases. All right? Again, we can get into the details here. It says it's caused by an increased nuclear charge. What that means is, hey, the positive power in the nucleus, there's more protons there to pull those electrons in, making it harder for those electrons to escape, or more energy is required for those electrons to escape. Now, as we move down a group, the ionization energy decreases. So again, as we move down a group, the ionization energy decreases, and this is because those electrons in those elements further and further down a group are further away from the nucleus, which is that pulling power of our atom. So as you get further away from that positive pull power, it's harder to keep those electrons in. Okay? Now, what we need to talk about in addition to this is why do some elements have a low ionization and why do some elements have a high ionization energy? And so we get to this, and this is really the start of our next chapter, but we introduce it here, and that is the Octet Rule. So the Octet Rule says, all right, elements want to gain, lose, or share electrons to get to 8 valence electrons. Why, do you ask? If we have 8 valence electrons, they fill their s and p orbitals of their highest energy level. What this does is it satisfies that atomic structure of that element, and they are, quote unquote, happy to have those s and p orbitals filled. Again, really this is the concept for chapter 8 and 9 when we talk about chemical bonding, but we want 8 valence electrons because they want to fill those s and p orbitals. So this right here helps explain why some atoms have high ionization energy and why some atoms have low ionization energy. Okay? What we can do now with that in mind, we can explain another trend which is known as electronegativity. Okay? And what we can do in addition to this, I should mention this, that ions tend to be gained on the right-hand side of the periodic table, and ions on the left-hand side lose electrons to be positive. Okay, so that will be emphasized later and later and time again. So let's get to this concept of electronegativity. All right, so electronegativity. Electronegativity is this. Is telling us the element's ability to attract electrons in a chemical bond. So in other words, it's saying, how bad do you want those electrons? How bad do you want to hold on to those electrons? Now, what we have to help understand how bad something or how bad an atom wants to hold on to those electrons is this Pauling scale. And he was a scientist, developed a scale, and each and every element had criteria it meant. And the scale goes from 0 to 4, 0 to 3.9 is actually our highest. And we will talk about the trend here in a second, but fluorine is the most electronegative. It's down here in the bottom left. Francium up here in the top right. Is the least electronegative. Oh, I flipped those. Fluorine, upper right, most electronegative. Francium, least electronegative. All right? And we'll emphasize that in our trend as well. So, bottom line up front with electronegativity is the more electronegativity or the higher electronegativity value an element has, the stronger it's going to attract those particular electrons. Okay? So let's talk about the trend for electronegativity. So the trend for electronegativity, as we move from left to right across a period, the electronegativity increases. That's why francium has the highest electronegativity value, fluorine. Fluorine has the highest electronegativity value. Now, as we move down a group, the electronegativity decreases. So this is why francium has the smallest electronegative value. Okay? And so if an element is in this upper left-hand portion of the periodic table where my finger is, that is considered an element to have a high ionization energy. And if an element's down here in the lower left-hand corner of the periodic table, it's considered to have a low ionization energy. Now, we don't rank the noble gases in terms of electronegativity because they form very few compounds, and so they're not wanting to gain and they're not wanting to lose electrons, and it all comes back to that octet rule saying that they have filled s and p orbitals. Okay, so the last things here, you don't have to write any words down. I just want to review our trends, and we start here with our atomic radius. As we move left to right in a period for atomic radius, the radius is going to decrease. As we move from top to bottom in a group, the radius increases, and that is for atomic radii. Now, ionic radii, remember, losing or gaining electrons. Positive ions from left to right, they decrease in that ionic radius size. Negative ions also decrease from left to right. As we move from top to bottom in a group, the ionic radius is going to increase. Our ionization energy, remember, ionization is saying how much energy is required to remove an electron from an atom. And as we move left to right, the ionization energy is going to increase. That's because elements on the right-hand side want to hold on to those particular electrons. And as they go down a group, they decrease because those electrons are further and further away from the center, from the nucleus of the atom. And then our last trend, what we just talked about, was electronegativity. So as we move left to right, the electronegativity increases, and as we move top to bottom, the electronegativity decreases. Again, this should say electronegativity decreases. All right, so talked a lot about periodic trends. We'll use these trends and make sense of them later on in class. As always, I hope you have enjoyed this particular episode, and if you haven't done so already, make sure you subscribe.